We're now going to talk about problem 2A, minimalist moles. And so this is sort of a word problem, but we can read it out. Mindy the mole wants to dig a network of tunnels connecting all of their secret hideouts. There are a set of few paths that between the secret hideouts that Mindy can possibly choose to include in their tunnel system, shown to the left. And so we can imagine the nodes are the secret hideouts, and all of these edges are representing the paths that they could possibly include to connect the secret hideouts, right? But some portions of the ground are harder to dig than others, and Mindy wants to do as little work as possible. In the diagram shown, the numbers next to the paths correspond to how hard that path is to dig for Mindy. And so we can imagine this path, maybe it's like made out of, I don't know, solid diamond, and so it's pretty hard to dig. Whereas this path is maybe, I don't know, made out of like very soft dirt, and so it's easy to dig. And Mindy wants to do as little work as possible. So how can Mindy figure out a tunnel system to connect their secret hideouts while doing minimal work? Take a moment, pause the video and think about it, and then come back when you have an idea. So this sounds like an awesome application for minimum spanning trees. A minimum spanning tree is going to make sure all of these secret hideouts are connected because they'll all be included in our spanning tree, but it's going to do minimal work because a minimum spanning tree guarantees that we'll have the least total edge weight or the least total work done in our case. So we're looking for a minimum spanning tree. That brings us to problem 2B, which asks us to run both Kruskals and Prims to find minimum spanning trees. And we're going to start with Kruskal's algorithm, and the pseudocode is included here, and we'll just run through the algorithm. And so the way Kruskals works is it says, well, there are still nodes not in the MST. We're going to add the lightest edge that doesn't create a loop. And then we're going to add the new node to the set of nodes in the MST. We can see what this means. So the idea with Kruskals is that you sort all of your edges and you're just picking them up in sorted order and including them or incorporating them into your MST, as long as they're not breaking the treeness of your MST, or in other words, not causing a cycle. And so just to start, we'll say, okay, there are definitely nodes not in our MST, right? Because we haven't included anything yet. And so we're going to enter the while loop. And then we add the lightest edge that doesn't create a loop. And so that's this one that we've bolded and highlighted in blue, which had a weight of 0. This was the lightest edge we could add, and it definitely didn't create a loop, right? The other thing is that we have to add the endpoints of this edge we just concluded to the set of our nodes in the MST. So we'll add both the endpoints C and E. And so everything colored blue is what's currently in our MST. But we come back up to the top of the while loop, and there's definitely still nodes not included, right? These nodes in gray are not yet in our MST, and we need to keep going until everything's included. So we're going to go ahead and add the lightest edge that doesn't create a loop. And so look around, and which one would that be? It's going to be this edge from A to C because it was the lightest, right? All the other edges were heavier, and it doesn't create a loop anywhere. Then we add the endpoint of that edge to the set of nodes in that MST. So A is now colored blue. We repeat this. And so we're going to add the lightest edge again, look around and see what you think it is. It's this one from E to F, right? Because it doesn't create a loop, and it was the next lightest one that is not yet in our tree. Then we add the endpoint of the edge to the set of nodes in the MST. And so F is now included in our MST. It's being like touched or incorporated, right? Then we keep going because there's still things that have to be included. And we're going to add the lightest edge that doesn't create a loop. So would that be this one because 3 is the next lightest edge? Not quite, because we want the lightest edge that doesn't make a loop. And if we included 3, we now have this cycle right here. So we're just going to move on and go, okay, what's the next lightest thing? 3 is a no-go. What's next? And that would be 4, this edge from A to B. And this does not create a loop, and it's the next lightest thing. We make sure to add the endpoint to our set, and we keep going. And so we add the lightest edge that doesn't create a loop. And so you're going to notice that would have been this one because it was the next lightest thing that does not create a loop. Then we make sure to add the endpoint of this new edge. And now everything is included in our MST. And so We have completed Kruskal's algorithm and found a valid MST. It connects all of Mindy's secret hideouts, or connects all the nodes in the graph, and it's of the minimum total weight. And so this is our MST, and we chose not to include these edges. Awesome. We're now going to run through prims and see if just how this different algorithm works. And so prims is a totally different approach, but also awesome. Prim's algorithm, we actually start with a specific node. And the idea with prims is that we start somewhere and we say this is our little set of things that are included, and we're going to sprawl outward, claiming more things into our MST until the whole graph is included. So we have our little set and we're sprawling outward in order, touching things as we go. And in that way, it's almost similar to Dijkstra's, right? Where we were like sort of crawling outwards and visiting things from what we know, like sort of stepping into the unknown. Prim's works very similarly to that. Whereas Kruskal's was able to jump around the graph and sort of just like go as it wanted to. Prim's is always going to be sprawling out from the start. And so we take A as our starting point here, as it says. And we're going to break ties if we need to by choosing vertices of lower alphabetical order. We actually don't need to break ties in this problem. But we're going to start with A, and we're going to add that to the set of nodes in the MST. So we're here. And now we're going to say, well, there are still nodes not in the MST. We're going to add the lightest edge that leads to a node that is unvisited. Or in other words, we're going to add the lightest edge that connects something that's in our MST, or something blue, to something that's not in our MST, or something in gray. Another way we commonly think about this is that the things in blue form a set of incorporated nodes, and the things in gray form a set of unincorporated nodes. And we want to find the lightest edge that crosses these sets or connects these sets. And so looking at these two edges that connect these sets, we want to pick the lighter of the two to include in our MST. And so we're going to add the lightest edge, which was 1, because when we had these two options, right, 1 is the lighter edge. And then we make sure, just like in Kruskal's, to add the other endpoint of that edge to our MST. And so that is one iteration. There are still nodes that are not in the MST, or nodes that are colored gray still. So we're going to once again add the lightest edge that connects a visited node to an unvisited node. Or in other words, something that connects a blue to a gray. We're sprawling outward. This is what we know. This is what we don't know. And we want to find something that connects that. And so the potential edges would be this one, this one, this one, this one, and this one. Things that are connecting this like little spoon to the big spoon, or however we want to think about it, connecting blue to gray, or connecting visited to unvisited, right? And so looking at all of these options I've highlighted, I see that this is the next best option. And so we're going to add this edge with weight 0 from C to E. And we, of course, add the endpoint. Now we continue our loop, and we're going to add the next thing that connects a visited to an unvisited. And so take a moment and think about what edge that might be. And we're going to see it's this one, because that was the lightest edge that connects something blue to something gray, or something included to not yet included. And of course, we add the endpoint. So now F's included. We continue going, and we're going to say, well, there's still nodes not in the MST. We'll add the lightest edge that connects blue to gray. And so I want you to notice that we're looking for the lightest thing that connects blue to gray. Although this edge from C to F might be lighter than a lot of the rest of the options, it's connecting blue to blue. Or in other words, we only wanted to see things that connect visited to unvisited, or connect this set to the unvisited set, right? And so things that like sort of cross this set would just be these edges, right? They break the boundary of our little set. And so we want to look at those options only. And we're going to pick this edge with weight 4, because it was the lightest of those 4 options. We add B because it's the other endpoint. And then we keep going. And we're going to add the lightest edge that connects something visited to unvisited. And so again, that's connecting blue to gray, or in other words, connecting something in our visited set to something outside of our visited set. And so of these two options I've highlighted, we would pick the edge with weight 5. And then we add this new node to the set of nodes in the MST. And all of the nodes are in the MST now, which means Prim's algorithm is complete. And we have finished this part of the problem. And this is our final MST. As an aside, we just ran both Prims and Kruskals, and both of them worked, right? They both found valid MSTs. They just had sort of different feelings to them. And so for a high-level overview of how I view the differences, Prims builds MSTs by dividing the graphs into two sets, those incorporated in the MST and the vertices yet to be included. And it continually adds the lightest edge connecting those two sets, sprawling outward and claiming more and more nodes into the MST until all nodes are included. Kruskals, on the other hand, builds MSTs by sorting all the edges and then adding each edge to our MST in order. But at every step, if adding an edge would cause a cycle, then it's just not included and we skip over it. And so Kruskals may jump around in the graph. Unlike Prims, which is like taking a starting point and crawling outwards in order, Kruskals is just taking the sorted edges and wherever they are in the graph, including them. And so that's sort of the flavor of the two algorithms, but both of them totally work. This leads us to the last question, which is, did Prims and Kruskals find different MSTs or the same MST? And is there a different tie-breaking scheme that would change your answer? And so we sort of already saw, right? They gave the same MST, which is this one. But for this specific graph, is a different tie-breaking scheme going to change your answer? You can take a moment and think about it. And the answer is no. No matter how we chose to break ties, it wouldn't change the fact that Prims and Kruskals are going to give the same MST because there was only one valid MST for this particular graph. All of the edge weights were unique. Notice there were no duplicates, which means there's only one valid MST. And because Prims and Kruskals are both correct, they're going to return the same only valid MST. If some of the edges were duplicates, there's a possibility that they might turn different MSTs if those duplicate edges meant there could be more than one valid MST, right? And so that is actually all of this problem. Thank you for sticking around and watching this video, and I hope you have a great rest of your day. Bye.